Alright, ladies and gentlemen, welcome back. We're going to pick up talking about chemical bonds today. So, when we talk about compounds, those compounds are two or more elements that are held together in some sort of fixed ratio. But what's actually holding those elements together in those compounds? Well, they're chemical bonds. And when we talk about bond formation, first off, these elements, atoms, are coming together to form bonds, and it's really their valence electrons that get involved in the chemical bonding. So when we look at your electron configuration, right, so here's a sodium atom, for example. Those valence electrons are those electrons that are on the outermost orbital, or the furthest electrons from your nucleus, right? And these are the ones that aren't getting shielded by anything else, and so as a result, they're the ones that are available to form chemical bonds. And those chemical bonds are ultimately what holds atoms together in a compound. Okay, so when we talk chemical bonds, we've got two major types that we're going to deal with, and those are your ionic bonds, which is going to be the topic for today, and then we'll also talk about covalent bonds in a later video. So, first off, why do we even bother going through chemical bonding? Why do atoms join up, make these compounds? Well, it really comes down to that they want to be as stable as possible. They want to be like your noble gases, which are in that very last column of our periodic table. So they're ultimately attempting to achieve a full valence shell. That final valence orbital of their atomic structure, they want it to be full of electrons. And remember that when we talk about electron configuration, that for most elements that means that they want 8 valence electrons in that outer shell. Except remember, we've got that exception with that first row where they only have up to 2. So your noble gases themselves, they've already got that stable electron configuration. Their outer shell is already maxed out. They can't put any more electrons there, which is why they tend to not exist in anything other than their own elemental form. They don't combine readily with other elements. Everybody else, however, is working to achieve that. They're trying to be like those noble gases. But the only way for them to actually get that full valence shell is to join up with other elements, with other atoms, and help each other out in filling that final shell. So let's take a couple seconds and just kind of walk through some shorthand ways that we can go about diagramming what that full valence shell looks like. So we're going to take some time and go through this particular table together. Alright, so if we take a look at this table, the first thing that we're going to notice is we've got a bunch of elements in that first column. We're then asked to determine valence electrons, do an electron dot diagram, as well as determine the number of valence electrons that I need in order to fill that element's final shell. So if we start off with boron, boron's our first element in the table. So boron's right here on my periodic table. First thing I need to understand in order to deal with this is how many valence electrons I'm dealing with in that particular element. And remember that our column number is what's going to tell me that. So boron is in column 3, so boron's got 3 valence electrons. Okay. Ultimately, boron wants to get a valence shell that looks like the nearest noble gas. And for that particular element, we're talking neon. So boron's here, it's got 3, I ultimately need to get to 8. So if I need to get to 8, but I'm already talking about having 3 inherently, that means that that boron needs 5 more to fill its valence shell. Okay. Now your electron dot diagram is a way to draw out, to model, to diagram how many valence electrons that particular element has in a single atom. Alright, and this is going to be useful when we start getting to drawing out how these bonding arrangements actually occur. So hopefully you've seen this before, but if not, just a pretty easy way to do it. So I'm going to take that element symbol that I have, and then I'm going to create dots for every valence electron that it has. And ultimately, every letter is going to have 4 sides, which means I can put a max of 8 dots around that particular symbol. So typically when we do this, alright, we start on one side, fill each side, and then go back and do the second dot. So boron's got 3, so 1, 2, and then 3. Alright, and the rest of those spots are blank because it doesn't have any more. Let's go down and do the next one. So Br is bromine, so bromine's right here. Tells me I'm in column 7, so 7 valence electrons. Closest noble gas is krypton. Alright, so if I've got 7 currently, I want to get to 8. That means I only need 1 more to fill that valence shell. And if I go back and do my dot diagram, I'm going to look something like this. So there's my Br. Okay, 1, 2, 3, 4, and now I can start over. 5, 6, and 7. Okay, so something along those lines. Just like we've been doing, take a couple seconds, pause that video, finish up the table, see if you can do it yourself, and then come on back and check out your answers. Alright, so if you double check your answers, this is more or less what you should see. So cesium's got 1, which means I need 7 to get to 8. Alright, all the way down to the argon there at the bottom, who has a full valence shell. It's a noble gas, and so won't need any extra electrons in order to fill its valence shell. So if we move on today, let's talk about one way in which elements can actually achieve that stable electron configuration if they don't already inherently have it, meaning they're not a noble gas already. So one option for some of the elements on our periodic table is to go through ionic bonding. And when we talk about ionic bonding, we're talking about the transferring of electrons from one atom to another. And typically, ionic bonds happen between a metal, which is on your left side of the periodic table, and a non-metal on the right side. Something like sodium and chloride, right? So this would be an example. And what I end up seeing is that when I take a look at my sodium atom, right, it's got 1 electron that it's then going to transfer over to chlorine. Okay? So in order for this to work, I'm going to end up creating ions. So remember what we were talking about before. If I change the number of protons, I change the element. If I change the number of neutrons, I create isotopes. But if I change the number of electrons, I create ions. So anytime that you've got the number of protons and the number of electrons not being equal to each other, there's no longer that charge balance, they're no longer neutral atoms, and as a result I've created either a positively charged ion or a negatively charged one, depending on what happens. So if I go back to my sodium chloride here, so sodium is ultimately going to lose 1 of its electrons. Alright, now in order for this to work, it still has to be 11 protons because it's still sodium, right? So if I go back to this picture right here, 11 protons, right? That's what makes it sodium, so that's not going to change. But once that transfer happens, I'm now down an electron, and as a result, I've got a positive charge. And so we talk about any positively charged ion, they occur because they lose electrons, and so we call them these things called cations. Anions, on the other hand, are ions that have now gained extra electrons, like the chlorine in this example. So they're negatively charged, they've gained electrons, so anions. So same deal, if I go back, alright, in order to be chlorine, I have to stay 17 protons, so that doesn't change. But when I gain that extra electron from sodium, I'm now up an extra negative charge, and that's where that -1 comes from. Okay? couple of ways you can remember anion versus cation. Alright, I happen to enjoy cats, so cats are positive to me, so that's one option. For those of you who aren't necessarily cat lovers, alright, that T is a plus sign. Okay, so plus positive, that's another way to remember it. So whichever one happens to work for you. Now when we're making ionic bonds, the atoms that are involved have to include at least one positive cation plus one negative anion. That's what ultimately then comes together to make an ionic compound. That being said, I can have two cations and one anion, or two anions and one cation. It really kind of just depends. But I need at least a positive ion and a negative one because ultimately it's those opposite charges that hold these guys together in that compound, right? So opposites attract. It's like putting a positive and a negative magnet together. That's what's going to keep those atoms together in that compound. Alright, so let's do a little bit more practice in determining whether or not, if I'm looking at my ion formula, did I gain or lose, how many, and does that mean that I'm dealing with an anion or a cation? Alright, so first thing I need to understand is the numbers themselves. Alright, and so let's start there. So number of electrons, what am I dealing with? So if I'm talking about oxygen minus 2, well, first off, that 2 is going to tell me how many electrons I'm dealing with. So I've got 2 electrons that are going on here. Then the question becomes, am I gaining those electrons or am I losing them? So what this is telling me is that oxygen has an extra 2 negative charges. Now remember that your electrons are negatively charged. So if I'm gaining 2 extra negative charges, I'm gaining 2 electrons. Okay, so in this case, this guy's going to gain. Okay. And if it's a negatively charged ion, remember that is your anion. Okay. Cesium plus, well, it's like math class again. There's no number it's understood to be a 1, but now I've got an extra positive charge. So in order to gain an extra positive, I can't change the number of protons because otherwise I change the element. So in order to gain a positive charge, that means I had to have lost an electron to get it. Alright, and positive ions are your cats. Alright, just like before, pause the video, take a couple minutes, try and finish up the rest of these, and come back and double check your answers. Alright, so hopefully these are the answers you came up with. The biggest thing is just to remember that those negatives mean extra electrons, positives mean they've lost them. So it's not necessarily anything super difficult, but a lot of kids, if they rush through these problems and don't think about it, immediately say negative means lost, gain means positive, because that's what you're used to seeing in your math classes. So just be careful with that. Alright, so let's walk through some examples. So I already sort of briefly talked you through the ionic bond that happens between sodium and chloride, right? We end up creating table salt or NaCl. And what we end up seeing when we deal with this is that that sodium ion only has one valence electron. So this is your metal on the left-hand side of the periodic table. And typically these guys are going to be the ones who end up losing those electrons. They get rid of them. Why? Well, because if I look at sodium, it's got one valence electron. It ultimately needs 8 to fill that valence shell, which means I'd have to go out and gather 7 more electrons. That's energy intensive. Alright? It's way easier to get rid of one electron than it is to have to pick up 7 more from somewhere. So rather than going out and finding those 7, it's just going to dump off that single valence electron. It's going to get rid of it, drop down to that inner shell below, which is already full. But this is matter. I can't create it, I can't destroy it, I can only put it somewhere else. So in this case, what's going to happen? Well, that electron ends up getting transferred over to a chlorine atom. Now, chlorine already has 7 valence electrons. I need to get to 8, which means I only need 1 more. So why do I want to have to figure out how to dump off 7 electrons when I can just go find a single one, and that's exactly what they do. So that sodium then transfers that 1 electron to that chlorine atom. Well, now that chlorine has 8 in its valence shell. It's happy, it's stable. The sodium's happy, it's stable. And now that I've got that sodium plus that chlorine, those two opposite charges are going to hold these guys together into our sodium chloride atom because those opposite charges attract each other. So let's spend some time actually diagramming out what ionic bonds look like. Alright, the more you draw them, the more you practice with them, the more hopefully these make sense. So let's kind of work through some of these examples that are in your notes. So the first one is between magnesium and sulfur, or Mg and S. So you're going to want your periodic table out if you don't already have it out, by the way. And the first thing I need to determine every time I'm diagramming a bond is how many valence electrons am I dealing with for the atoms that are involved. So in this case, if I take a look at magnesium, I find it on my periodic table. I'm going to find that it's in column 2. Remember that column number tells me how many valence electrons I'm dealing with. So magnesium has 2 valence electrons. Find sulfur, it's going to be in column 6, so 6 valence electrons. Once I've determined that, now I can decide, alright, based on their position on the periodic table, how many valence electrons do they have? How many more do they need? And is that going to make one ion the cation, which is going to be the anion? So magnesium is going to ultimately be on the left-hand side of the periodic table. These guys are the ones who are going to want to lose those electrons. And so magnesium is going to lose both. Alright, which makes it positive, and so that's your cation. Sulfur, on the other hand, is going to gain those 2 electrons because it needs 2 more. And in gaining those electrons, it's going to become more negative, and so that's where your anion comes in. Okay, now, I want to see what these guys look like before anything happens. Okay, before the bond ever even occurs, before there's any transfer of electrons. And in order to do this, I'm going to do those dot diagrams like we were practicing earlier with just a slight adjustment. Alright, so for my cations, I'm going to do my dot diagrams, but rather than just doing dots, I'm going to use open circles. Alright, and this is going to help me be able to see where these electrons go once we actually get to the bonding in a couple minutes. Your anion, on the other hand, is going to look just like we were doing before. Alright, so magnesium's got 2 open circles because it's got 2 valence before anything happens, and your sulfur has 6 closed dots, 6 valence electrons. Now I've got to determine, well, how many electrons are going to transfer from one atom to the next. So magnesium is my cation. It needs to get rid of 2 electrons. My sulfur is my anion. It needs to gain 2, and so in this case there's going to be a net transfer of 2 electrons going from magnesium to that sulfur. Final step is to actually show the diagram of the bond itself. Okay, so the magnesium in and of itself is going to get rid of those electrons, which means it shouldn't have any dots left. Where are they going to end up? They're going to end up on that sulfur, and so it'll look like this, and then we use some arrows to show that transfer so we can see where they started to where they go, and sort of just show that these guys are now connected in a chemical compound. So let's walk through another one. Lithium and fluoride. So Li, lithium, is in the first column, so 1 valence electron. Fluorine's got 7 because it's in column 7. So if I look, Lithium's on the left-hand side of the table. It's going to need to lose that one electron, becoming positive, so that's your cation. Your fluorine is going to ultimately gain one electron. As a result, it becomes negative, and so this is your anion. If I draw these guys out before anything happens, right, lithium's your cat, so it's got the open circle. Fluorine's got 7 closed dots because it's your anion. Lithium's going to need to transfer a single electron to fluorine, become that anion, and so your final diagram will look something like this. Alright, so at this point I encourage you, just like we've been doing, pause the video, work through the rest of the ionic bond examples, and then come back and check your answers. Alright, so if we try the next one, now you've got 3. So were you able to figure out what you needed to do? Well, Sr, strontium, 2 valence electrons. Your bromines each have 7. So, what does that mean? Well, strontium's going to want to lose those electrons, and it's going to want to lose all of them. So it's going to still be your cation. Bromines, on the other hand, they're only going to be able to gain 1 apiece, but they are going to want to do that, become negative, and so those are your anions. So if I draw what this looks like before any bonding happens, there's my cation, my Sr, two dots, and my 2 bromines. I need to draw both of them. I've got 2 this time. Alright, and they both have 7 closed circles. So here's where it becomes a little tricky. That strontium, that Sr, is your cation. It needs to get rid of 2 electrons, but it's only going to transfer 1 electron apiece to each bromine. Alright, and so ultimately it looks like this. Okay, so your strontium, realistically you could put it anywhere, just so long as you're showing where those open circles are going, and each bromine picks up 1 of them.